Welcome to this hands-on session. So what we are going to do is that, so first we will install CASA. That is the software, basically common software application, astronomy software application. Okay. So we'll install CASA, and Abhinav will help you to you have downloaded the file, right? So install CASA and install also the this thing, right? Docker. Docker thing also you install, and then what we'll come back to the data and how the data looks and so on, right? So Abhinav, you take over and help to install the CASA, and then we'll come back.
Okay, so first we'll look at CASA installation. So I hope everyone has downloaded the contents of the drive folder. So there you'll see this tar file called CASA 6.620, this thing. So first you untar it.
Also, if some people already know, they can help the nearest neighbor.
You have downloaded the tar file and untar it first. Okay, so if anybody is having any issue with Docker, just know that you won't have to use Docker. So if there are any issues, wait till time, and we'll resolve all of them.
So after you untar the CASA tar file, this folder will be there called CASA 6.6, this thing. So have you untarred the CASA file? Once you untar the CASA file, this CASA 6.6 folder will be created. Enter the folder, and inside there will be a bin folder. And this is where the CASA executables are, essentially. So you can actually check if it's running or not right now. Just run this CASA thing. And this window will open. So this path in which all these executables are located is where your CASA is. Now what we're going to do is we're just going to put this inside the bash so that you can access it from anywhere in the terminal. So if you go to your home and you open your bash RC, just open the .bash RC folder of file and add
So there are, I think, 4 or 5 volunteers. Who are the volunteers? Just raise your hand. 1, 2. Rashmi? Yeah, so if you are finding issues, you can ask these people, right? Okay. And also otherwise there, yeah. So 1, 2, 3, 4, 5. So we have 5 people. And I guess some people are also aware of CASA and all those stuff. So, okay.
So the path of where the CASA is, which is inside the CASA folder and the bin folder, you just need to add this as the path inside the path variable. So just add this line, which I have added at the end of this file, inside the bash rc file. The bash rc file will be in your home, called dot bash rc. And then just do source bash rc. Now your CASA will open anywhere. So it's added to your path, and you don't need to go inside the folder and do all this. Inside the documentation, there is another method which is written, and which is that you can just use the alias way. You can just make an alias of where the CASA is and add that to your bash RC, and then also CASA will work. Now, if you type CASA and this whole thing doesn't come, like this window doesn't open, this is the logger, then we have a problem. Then we can try to fix that. This is what CASA looks like. सूडो चाहिए नहीं सूडो नहीं चाहिए सूडो को बिना नहीं चल रहा है सूडो डालेगा तो हाँ तो उसके लिए हम लोग को पास वो बनाना पड़ेगा वही करते हैं अभी
अभी डॉकर नहीं चाहिए ना, लेकिन लंच मैं वही बोल रहा हूँ, लंच तक तो उन लोग को नहीं चाहिए डॉकर।
फिर भी अभी बोल देते हैं So how many people have managed to make CASA open and it's working? So in the bash RC, this is okay. So bash RC is in the home, and at the end, just add export path equal to whatever the path of your.
You want to add this path to your data. The last one, export path. Otherwise, you will be unable. No, so tell them how to get that path. Go to that directory and then directly open another.
So this is where, okay, so this is where your, when you untarred the CASA file, it made a folder, right? And this was the folder CASA 6.6 something something. And inside the folder, there is a bin. If you do PWD here, you can see the path. So here the path is home, Kirti, radio tutorial, this. This, just copy this whole thing. And then add it here to your bash RC. You see export path equal to this, and then colon dollar path again, so that your path does not break. And then save it and source.
They are working on a data.
तो भी चलेगा। technically पता नहीं, मैंने यूज नहीं किया मैक कभी। So how many people still have a problem?
Everyone, raise your hand. Is there anyone who will not seeing the logger after opening class? So everyone has been able to answer the thing, right? Then you can go to the directory where the Kasa is at by doing cd and then cd bin and copy the path. So show it once.
So this is okay. You untarred the casa and it made a folder, and just go into the folder. There's a bin. Inside the folder, there's a bin, and just do a PWD and just copy this whole thing. This is where the path.
You can print all those logger. Are you also you was able to open to your data? What will happen is that it will not open the logger, but everything will be printed here in your time. So minus the log two term is basically saying that you print the whatever will be stored in the logger instead of storing there, basically printing here. Okay, let me ask you. This is a new problem. They have this new system.
So how many people have managed to, like, at least open casa? It's opening. If the logger is not coming, we'll see.
There are issues like with fuse, FUAC.
libfuse. You
Yeah,
install
so
it. Then
most
it
of these people they don't have. They are unable to open the GUI.
Okay.
Like the
So
log,
to open the GUI, you might need to install two libraries.
but they are unable to install those. The fuse, FUAC.
So just
UWPT install libfuse2 and install the tape.
But you need sudo for that. Some people they don't have sudo. They are
क्यों?
खुद के machine में नहीं कर रहा है शायद. हाँ.
सुडो नहीं तो कुछ नहीं चलेगा.
तुम एक बार बोलो ये अपन माइक इसका फ्यूज का प्रॉब्लम है. Why are you?
So how many people here have opened casa but the logger is not opening?
Is there anyone who can open Casa but no logger?
The logger doesn't come.
Okay.
And how many people have, like, it's working? Like logger is working and everything. सुडो नहीं है तो कैसे होगा भाई? अभी डॉकर वॉकर कैसे डालेंगे ये तो बिना सुडो नहीं? तो
लैपटॉप में तो खुद ही शुरू
हाँ पता नहीं, अगर एडमिन नहीं है तो कैसे होगा? अच्छा इंस्टॉल नहीं कर पाएगा?
just 1 hour. There are two people who are नहीं हो रहा है। खुद के मशीन में कोई काम नहीं कर रहा है।
कुछ लोग तो कर रहे हैं, सभी नहीं कर रहे।
Why not? Where you have to do? Actually, you need sudo just to install the other software using Docker. So, yeah, if you have a machine where you have sudo, then that is fine. If having issue, no problem.
Okay, so if you have Casa working, then okay, so
Hello, hello.
okay, so there are two files that were in the drive folder. There's the raw data and the calibrated and clean target. Today we are going to work first on the raw data and show you how to calibrate it and clean it and basically give the finished UV products that we can image later. So the raw data is in the A3376 raw data.tar, so untar it. And so this,
No, just everyone able to enter the data or finished entering the data?
so this file will be file will be created called 21.5/2019 GWB. This thing. This is the MS file that we are going to work with. Now, if you open the documentation that we have shared, there's the then you could begin reading it and start working on this. So essentially, if you open Casa here and open Casa here, and you can see the details of this observation by using list stops. List stops is one of the tasks in Casa. Just type list stops and the name of the file in single quotes. And
Now you can actually keep the PDF file open in some.
yeah, so open the PDF file that you've shared, all the details of how to process and all the details of how to use Casa is written in that PDF file. In the logger,
But then I think they should find out what is the calibrator. यहाँ पर calibrator target कैसे data लिया?
लिखना है उसमें।
No,
PDF
no, they
file
should
खोल
do
के
it.
पढ़े तो।
पर नहीं पड़ेगा. We should need to demonstrate that.
If you have done list stops, then this logger will display all the details of this observation. So from here you can see this is an observation which was done on 21st May 2019. Started at 6:40 something, ended at 12:40. 6-hour observation of A3376. So basically the format of how the data looks can be inferred from here. inside this MS file, this observation, there are 3 fields: 33147, 0538 and the target, which is called A3376S3. So A3376S3 is one of the pointings that we've used to image the Abel3376 cluster. And I mean, all these details are in the PDF file. So essentially, this file has 256 channels, and the central frequency is 1360 megahertz. So wideband data 200 megahertz. And these are the details of all
Also-
the antennas essentially of GMRT.
Yeah, also the channel width is basically negative, but which is not negative, right? It's basically they count from the end to the beginning. Like your bandwidth is this big, they count from the higher part to and go to the lower part.
Yeah,
That's why it
basically
is
the
negative.
data is arranged in the opposite kind of
Yeah,
manner.
in the
So that's
opposite
why
direction.
channel width is negative. That is not a problem.
So as you can see that channel 0 is 1459 megahertz, and they count the fast channel is the end part of your band, and then they go to the lower part. So that's why the channel width is negative. And you have two correlation, RR and LL, which is basically right and left, or basically the two polarization. And the total bandwidth is 200 megahertz.
So now we can just do a simple plot of this data. So if you type plot ms, this window will open.
Process slow. Give some time.
Okay, so how many of you have been able to run list stops? Yeah, I need all the hands up. So, okay, so who are not being able to run? Raise your hands. Acha, ekdam back mein.
And he is helping. Okay.
Acha, he is there. And who else? Some hands from this side. Not being able to run the stops.
You guys are unable to. Okay.
Done, no?
Oh, all are Mac. Okay. You are unable to do list stops.
In the second row, everybody has been able to run this thing.
So I suggest everyone
Which-
open the PDF file, the
List of
instruction
fun one.
thing.
Why is it in Casa?
You can keep the PDF file open in a separate window and like keep reading
Have
through
you
it.
added the path to the bin to your basher C? No, you. Yeah. No, that is fine. Terminal A. So you are able to open.
Yeah, it was open.
Where is the data?
It is in documents. CG documents. Then video. ID. Here, yeah, basically extracted the data.
Okay. So what we do typically make a data move. Which one is the this one, right?
That file is in the CASA directory. So you from there.
Yeah.
Okay, so I can
Move
Well,
that
yeah,
thing
na?
here. Close this casa first. The data. No, not here, not here. You move this thing to here, like documents, radio analysis. Documents, radio. Now go there. You're already there. Go to data. Open CASA. Now, that is fine. Don't close it. Go to the terminal. List stops within that file. No, you can actually, you can start with this and make a tab. What is the name?
21. Okay. So it will automatically detect
Yeah.
everything. Okay.
So if you now open the, where is the logger? Yeah, it is here. Now you need to just go up. You can read, like it is being observed this time. These are the field like 33147, etc. And every field has a unique ID. 3147 is 0. 05, this is the phase calibrator, it has 1, and another unique ID for the target. Target is your level. And it is observed for different scan. We will cover that one. And this is the bandwidth information.
Okay, yes, sir.
And if you just go here, this is actually Python terminal. You can do anything here. Right?
Sure, okay.
So you can do LSA, let's say 2 plus 2, whatever, like 2 plus 2 plus. It is basically a Python terminal. So you can do anything here. Are you guys able to? No, don't work within CASA. So move the, no, not this one. So typically what we do is something like this. So we make a directory here, data, CD data, and where is the data actually stored?
Here. CASA, there is this directory. Capital.
So you create a directory which is outside of CASA
Okay.
and work there. That is the best thing to do.
Okay, okay.
Now,
CASA is already running.
you need to use this one. And now you are actually in the, and this is actually a Python terminal. You can do ls also. Okay. And you also have a, you have the logger file, right? So you can now do list.
So list
Of-
of basically list of observation.
Yeah, list of is basically showing that if you do list of and your data file, so this is your data file.
Okay,
Dot-
so
that list, whatever.
People,
inside the data.
if you guys are being able to do list offs, so let us look at what it gives. There are certain information which regarding the observation is there. So if you have done list offs, so please open this list offs output in the log file. So we will just take a look like what kind of information it is giving. And I will tell you about like, what are the observations, the way it's actually done. So everybody has done this list offs, right?
No,
right?
First, you need to enter this
So-
one. This will come later. The raw data one.
Yeah, so if you can see, look at this part,
Yeah, what the data
this,
Eco.
this part, okay. So this is basically telling you about the scans, okay, different scans. So, so when we perform radio observation, okay, so it is not like, you just look at the target source and do the Fourier transform and get the image, okay. So there are certain other things we have to do, because you see the radio telescope, I mean, ultimately it is going to measure the electric field, right? But then the currents, whatever you will get, that is like very small. You need to amplify them, right? It's like the currents are in microampere. If you calculate the strength of the electric field and the kind of current they will induce in your, this measurement device or in antenna, they are very feeble. So you need to amplify those signals, right? Then you will also, condition this signal because like you only are interested in some part of the frequency, right? Sky, the radiation is coming, all the frequencies are there. But you will be, depending on your science case, only some part of the frequency you will be interested, right? So there will be filters. So all these electronics component will be there in your measuring. So now I can ask you, let's say I have two amplifiers, which is like amplifying the signal current, right? But one amplifier has a higher gain. Let's say it is amplifying 1000 times. And the other amplifier is doing like, 800 times. So now when you calculate the electric field, this will be wrong, right? Because the electric field is amplified, and if you do not know the gains, you are not sure like whether the electric field is from the source is more or the amplification is more, right? So you need to have a process of calibration, correct? So when you are trying to calculate this electric field, so you need to have a source of calibration. Somehow you know that, okay, you can calculate the gain. So for that, what the observation strategists do is that they observe some standard source for which we already know what is the flux value. Okay, so there are certain sources in the sky present, like 3C147, 3C286, and so they are like really bright source, and their flux is very well measured. So I know that this source is 15 Jansky source or 20 Jansky source, and it does not vary with time. I mean, now if I measure that it is 15 Jansky, even if I come back after 10 years, that it will be 15 Jansky. Okay. So then you observe this source at the beginning of your observation and at the end of your observation. Okay. Why? Because so if I observe it like first, and then I know this is like 15 Jansky, then I can calculate back my gains of the amplifiers, right? That is fine. And then, but what happens is that these amplifiers, the gain of the amplifiers, they are also not static. See, they are like electronic devices, right? So they also change with temperature. Even if you set the gain at certain point, it may slowly, decay. Depending on other other effects, for example, temperature and other things, right? So you know that, okay, when I am measuring the source calibrator, this is my gain, right? But then at the end of your observation, which is like 10 hours later, this gain might change. So what you do is that you measure at the beginning and you also measure at the end, right? So you calculate the gain over here, you calculate the gain over here, and you assume that this variation is smooth, okay? And then if you know that, okay, here the gain was 800, here the gain was 1000, let's say. So you can find out a function which can smoothly from 800 to go for 800 to 1000 in 10 hours observation, right? So that is why you will see at the beginning and at the end of any observation, you will find some calibrator source, which is like bright, okay? They are called flux calibrators. So here you see this, now if you see the scan, you see this source, this 3C147, okay? Everybody can see, right? So this is a calibrator. This is at the beginning and you see at the end of the observation. So these are like different scans. And our target is this guy, A3376S3. Okay. Now there are others, one more sources. This is 0538440. Okay. That is called phase calibrator. Now if you remember the equation we have worked out, you see, we have done all this complicated calculation of this difference path to calculate the phase term, right? That how much phase difference would be there in that correlation. But this signal which is coming from the sky, it is passing through ionosphere. It is passing through ionosphere, right? This ionosphere is what? Is basically a plasma or layer of charged particles, correct? What they do is that they induce a phase. So if say for example, I have a radiation which is passing through a plasma screen, so the amplitude will not be changed, but my phase will be changed because the refractive index of that plasma is different. Okay, so when all this radiation, this radio waves which are coming from the sky, and you're going, one part is going your antenna 1, and then another is going in antenna 2. So these two rays, this wave front is looking at different ionospheric patch, correct? It is, say for GMRT, is, anybody knows like how much is the spread of GMRT? GMRT is spread over how much region? It has 30 antennas, but what is the area? Like this thing is about 25 kilometers. Okay, so you can't expect the ionospheric condition here and 25 kilometer apart same. Okay, it would be different. So it means these two rays which are like going through these two part of the thing, they will go through different phase, right? So the phase change, the refractive index over here and refractive index over here, they are different. So when it is different, the same ray, when it is before atmosphere, it is all like plane wave front. Okay, but once it goes into the atmosphere, this ionosphere, and then come out, then here it might be 10 degree, here it might be 20 degree, correct? Then this is a problem, because you remember we have only corrected for the path difference from the antenna location. These extra phase we have not done anything, and we do not know it because it changes, ionosphere is changing. So then what you do is that you find another calibrator which is called phase calibrator near to your source. What is the phase calibrator? I know the phase calibrator is a point source, right? Now if it is a point source, from the point source, the wave front will be like plane wave front, right? If my point source is a point source sitting at infinity, so definitely before it enters the ionosphere, it will be a plane wave front. Now after the atmosphere, right, it is getting hindered and then coming to my antenna, two antennas. Now if I look at the phase of this antenna and this antenna, I know this is my calibrator, so it has to be like a point source, so it has to be same phase, but I will see that there is a 10 degree phase difference. So that phase I will correct for, okay, to correct for this ionospheric problem, right? So now this point source has to be close to your target, because you see, let's say my target is here, correct, and my point source is there. So this point source will basically trace the different ionosphere as compared to this. Then those solutions of this will not actually be applicable over here. So I need to find out a phase calibrator which is reasonably close to the target, such that I can assume that okay, itna difference hai, but within that difference the ionosphere is almost uniform. So if the 10 degrees difference is coming into my target, this phase calibrator source, the same 10 degree will be applicable to my target source also. Okay, you see target sources often, no, I mean almost all the time they might not be point source, they would be a distributed source, and for a distributed source the wave fronts will not be a plane wave front, right? Distributed source means you can consider distributed source like a combination or a collection of point sources. Now each point source will have its own plane wave front, so it will be a sum of all of them, right? So the target is target, you cannot use that as a calibrator. So you will find a phase calibrator which is reasonably near to the target, and then you will look at this to calculate the phase correction. Now ionosphere typically changes at the order of like half an hour to 1 hour, 1 hour time scale. So it means that you have to find out those solutions every 1 hour or 45 minutes, okay? Because every 45 minutes it is now different. This 10 degree has become 15 degree, right? So that's why you will see, if you see this scans, so the flux calibrator here and here at the beginning and the end, okay? Then you have this phase calibrator which is like sandwiched between every observation. Why? Because these phase things actually vary reasonably quickly. Now it is 10 degree, after 1 hour it might be 15, after another 1 hour it might be 20 or so. So you start with flux calibrator beginning and the end, then you have phase calibrator, source, phase calibrator, source, phase calibrator, source, right? So when you look for this phase solution, so you solve, so you have solution, you 10 degree, 15 degree, 13 degree, whatever this thing, and then you make a polynomial fit to find out the phase difference when you have observed the source. Because when you are observing the target, that time you are not observing at the same time the flux phase calibrator, right? So the solution, when you are observing the target, is not present at that time. So you basically interpolate, I mean, in a sense, right? So that is why this is the strategy of the observation. You start with a flux calibrator, end with a flux calibrator, then between every scan of your target source, which is like A3376, this is a cluster basically, which is not a point source at all. You observe your point source, which is reasonably close to your target, in every like 45 minutes. So this is clear to everyone, the strategy of the observation. So in every observation, you will see not only the target, apart from target, there are two other sources which will be observed. One is the flux calibrator, another is the phase calibrator. Now you can ask me that why the phase calibrator cannot be used as a flux calibrator, let's say, right? The problem is that when you are working out the gains, okay, when you are working out the gains, you would like to minimize the errors. So you need some source which is like very strong, 15 Jansky, 20 Jansky source, then your gain solutions will have less error. So you are reasonably confident that the measurement, the gain solution measurements are like correct. But this phase calibrator is they are mostly like not as strong sources, because you see you have to find out these sources very close to, like, all over the sky, right? Your target is here, so you need to find out a close by phase calibrator. My target can be here, I also can have find out some source over here. So these phase calibrators are generally not very high flux sources, but they are point sources, right? Now because we are only care about the phases, okay, if you get a bright phase calibrator is good, okay, but not necessarily you will always find a bright phase calibrator. So that is why the flux calibrator, just to minimize the gain error, because we are just measuring the flux now, so we are just measuring the gain there, we are not actually worried about the phases. So it can, as bright as is fine, it can be far away, that is okay, right? But phase calibrator, you have to make sure that it is actually close to the source within about 10 degree, so that it really does not I mean, it patches, it samples the same patch of the ionosphere, right? So this is the strategy. So this is your the scans. Now you have these three sources. The information about these three sources are there. Then you have the frequency information of these three sources. Because as I said, that you can selectively choose that which part of the frequency you are interested in, and you can set the observatory frequency setting. You can do that, it will only select data or collect data within that frequency ranges, okay? So this is okay. And then we have this antenna IDs. Basically, in your observation, like for GMRT, we have like 30 antennas. So it gives the information about antennas. You see, we were discussing that the antenna coordinates are very important, right? To calculate UVW. You see that, these antenna coordinates are given in this three, like this east, north elevation. So these are like in a ENU unit. So you have antenna location and antenna numbers and so on and so forth, right? So this is basically gives you a brief idea about what the observation has been done, the basic kind of parameters of the observation, okay? Starting from, so we have also the frequency information, SPW somewhere. Here you see the frequency ID. Yeah, so it says that it has like 256 channels. It has 256 channels. Then you have this channel 0 frequency is 1459 megahertz. Then total bandwidth is 200 megahertz. Increment of the channel is minus in frequency. So it's just a convention. You can count your channel 0 here, lower frequency, and say that my channel is increasing in the right direction with a positive thing, or you can say my channel 0 is at the end channel and my frequency is increasing in this direction with a negative sign. This is just convention. It's not a problem, okay? And central frequency is like 1360 megahertz and so. So this is basically an overview of what is the frequency setting we have done, right? Then I will show you this. There is something called plot MS. Now this is the frequency information, scan information, and all this all fine, right? Now you can also see what we have recorded. We have recorded this E star, right, as a function of UV and this thing, right? So that is the visibility we have recorded. So this E star is a complex number, right? So it will have a amplitude and phase, correct? So now let us plot this thing. Let's say we do plot MS, correct? So plot MS will pop up a window like this. It is basically plots the visibilities in a different way, right? So you see, I have many different parameters in the observation. One parameter is the target, the source. The source could be 3C147, my target, or phase calibrator. Then each source might have different scans, like 3C147 is observed at the beginning, at the end, right? So it can have different scans. It can have different frequency also, right? Because I have 256 frequency channels. So all these parameters, different way I can plot. I can plot like as a function of frequency. I can plot as a function of time. I can plot as a function of scan. I can plot as a function of different source also, right? So typically in the first look, what we do is that you browse and say this is my MS file. So I choose MS file. Okay. I do not want to plot all the channels at a time, because if you plot, so this is like 3 GB of data, but typically GMRT data will be much larger, let's say, tens of GBs. So if you plot like all channel all time, it's a huge amount of data to load in RAM, right? So I will first look at, let us see one channel, how it looks like. Okay. So I can select that doing SPW0 : I have 256 channels. Let I plot the middle one, 128, right? So this is telling SPW0 means, some telescopes have this, even GMRT also have this thing, that at the same time you can record in two frequency bands, let's say one band, other band at the same time with different, backend is capable enough to doing that. So in that case, not to confuse you, you label one as spectral window 0 and spectral window 1. If you have more, you can, spectral window 2, spectral window 3, and so on. But here we have only one spectral window. Okay, is selected range. We have not recorded into like multiple way. So that is why this is like only 0. So if you have like some data where like you see, so in that log thing, if you have multiple, then you will see not only one line. There will be 0 spectral window, which has a starting channel, ending channel 256. Then in a spectral window 1, which will have starting frequency different, ending frequency different, and like that. Okay. So this is 0, 128. Then let us look at axis. So this axis, you have like multiple options. You see over here x-axis. Here I have selected time because I want to see that as a function of time how it looks like. You have field, you have scans, you have different things. With experience, you will realize that what is important for looking at what. Then in the data column, you see here I have different things. You see, I have amplitude, I will have also phase, you see. Then there are different things, real part, imaginary part, weight, and so on and so forth. But for the just timing, we are looking at amplitude. Okay. Amplitude means what is the total power is coming, right? Then you have page. Page means this is like iteration. Now you see I have 30 antennas, correct? Now these 30 antenna can pair in different way, 1, 2, 1, 3, 1, 4, 1, 6, like, right? So when I talk about, I want to look at as a function of time and want to look at the amplitude, then the next question comes, for which antenna, correct? Which baseline, or like, which source.
So there, this page lets you select that iterative. So if I say that, okay, let us look at antenna wise. I want to find out some bad antenna is there or not. So let us look at antenna wise. So what it will do, so if I select this axis as antenna, then it will show one antenna at a time, right? So let us do that. Then if you say plot, right? So you see, this is antenna 1 whose name is C00, and the first scan. So these are like, you can see that, you know, scans as a function. So x-axis is time, right? And y-axis is amplitude, correct? If I may just enlarge this guy. So x-axis is time, y-axis is amplitude, right? What we have done, we have discussed this thing, right? So the first scan was 3C147, that is a flux calibrator, which is a very bright, strong source. Now, can you see the amplitude of this source is much higher than all this other thing? So at the beginning and at the end, you see this is much high, you know, quite high. The amplitude is high, isn't it? Right? And then you see these scans. This, you know, say this. My cursor is visible, right? So these scans, these are like every alternate scans here. These guys. This. So this is phase calibrator. This is not as bright as that guy, but this is brighter than this guy. And this is our target. Okay. So now if you see, it actually makes sense. At the beginning, we have observed flux calibrator, which is brighter. Then we have started with phase calibrator, little bit less bright. Then target, phase calibrator, target, phase calibrator, target, phase calibrator. And then at the end, we have obtained the flux calibrator again. Up to this point, it is clear, right? How the observation is being done strategically, right? Now, yeah.
Another thing you can do is colorize in the. Yeah. So in the display, there is an option of colorize, and you can colorize by field, and you can plot it again. It is basically showing the same thing, like the black is flux calibrator. And
yeah. So if you colorize as a function of field means different sources basically. So then it will colorize different source in different color. So you can see this is both are black, right? So it means that those things are coming from the same source. This is coming, these reds are coming from the same source, other source, which is like, phase calibrator. And these are the same other sources. Okay. So this is interesting, right? Now, if you can, here there is this arrow key, okay, niche. So if you hit this thing, so it will go to the next antenna. Now this is C1, earlier it used to be C0. Now you can see it is C2, C3, C4, C5, C6, now comes C8. Now, do you see some problem with this guy? Right? The flux should have been there, right? But it's all 0, 0, 0, 0, 0, almost 0, right? This antenna wasn't working. You have 30 antennas, right? These are big antennas. There are a lot of electronics, power, n number of things, right? But at any point of time, it is not necessary that all the antennas will work. Some antennas may be down, some antennas maybe painting work is going on. So you can see this antenna is almost dead and it came up at the end, right? But the problem is that we won't have the calibration thing, right? Because it's almost dead. So what we'll do is that we'll actually flag this antenna. We'll exclude this antenna from our analysis. What it will do is that you have this UV visibility points, right? For Fourier transform. Some of the points will be gone from there, but it's okay. It's better to flag bad antenna rather than keeping antenna. So this is basically the first step. What you have to do is that keep going like this and identify dead antennas which are actually not working, right? So here also you see some part it is gone. This is which one? This is C14. Some part it was fine, then it is gone. then maybe at some time it has come alive, right? So like that. And there is another antenna, I think S6. Yeah, you see this antenna S6, this is like bad throughout. I mean, it has all these sources have like on the same scale, how it can be, right? Because this source is much brighter than this source is much brighter. So this is basically recording the noise, recording noise. So this antenna is dead throughout. Okay, and you can also look at the Y scale amplitude. This is 0.05. If I can go back to the previous antenna, look at the Y-axis. It is 2, 6, 10, right? But in the next, you see it is 0.05. So this antenna is dead throughout. So you have to kind of get rid of this antenna. Okay. Yeah. So you have to iterate over all the antennas. So this is W2. Then we have kind of found 3 antennas. Here also, W3 also has problem at the end, as you can see. Okay. So this we have to strategically kind of get rid of these guys while doing this thing. See, remember, this imaging thing is a Fourier transform, right? So it means, to get one point over here, you have to have information on all the points. So if any point is bad, it's going to create, badness in all the points over here. So you have to be very clear that you do not have any kind of, nonsense sitting over here, because it's a Fourier transform. You will be going to integrate over all the points. Okay, so that's a problem. Okay, so you have to be very careful in that, right? So W3, W4, W5, W6. Okay, so we have, roughly we got like about 3 antennas, which has, critical problem, and that we will actually flag those antennas. Okay, that will kind of get flagged. Okay. Right. Okay, so any question? Do you guys have any questions regarding? Sorry? So that is a number, 30th antenna. Antenna 1, antenna 2, antenna 3, but each antenna also has a name, C for central square, W for west wing. And so, it has just, this is just W6, but this is 30th antenna. Like that, C0, first antenna, like that. Right? So any questions? Okay, so the task is that you guys should find out the dead antennas for this observation, and then let us know which one to flag. Okay, so one thing what I have missed is that so there are 2 polarizations. Okay, generally when we talk about electric field, the electromagnetic radiations, they can be polarized also, right? So you have this antenna when you are recording this electric field, so you can record both the polarization. If you place your conductor like this, you will pick up one polarization. If you place your conductor or the dipole like this, you can pick up another polarization. So typically in GMRT, you also can have like this circular feed also, okay, which can pick up like right circularly polarized light and left circularly polarized light. And these 2 polarization, as you can imagine, that they will be completely different signal chain, because this polarization will induce some current, this polarization will some other current, right? And some sources on the sky may be polarized. They may have some in a polarization particular direction. So this feed will only have current, but not this. So this is completely different chain, different amplifiers, different filters, and so on. So you have to treat them like, coming from 2 different antennas or so. So it might happen that one polarization signal chain is dead, some amplifier is bad, but the other polarization is fine. So you can plot this guy as a function of polarization also. Okay, so this is given by this data selection, this correlation. You see this is CORR. Okay. If you don't mention it, it will basically do a root over of RR square plus LL square. But you can also do like this, that is right circularly polarized light, and you can say go. Okay. Then only it will plot the right circularly polarized thing. Okay. Yes, now you see it's a thing. So when we are doing flagging the bad antennas, okay, we have to look individual RR and LL, because in some cases, as I mentioned, that RR might be bad, but LL might be good. It is okay, right? So then we don't flag everything. Okay. So now this is your task quickly. I mean, of course, we have already found out and given in the document. But you know, if you want to play it around, so you can just go through. It will be quick actually. Just take a look and kind of get a feel like which antennas are bad, which should be flagged, dead antennas basically. Okay. So it's fine. Clear?
Just locate के बारे में बताओ.
Okay, so one more thing is that let's say I find yes, okay, fine. So then let's say here I have this C04 antenna, but I can also kind of locate. So when I'm looking at this visibility, it sometimes may not be very clear to me that which antenna or which baseline it is coming from. Okay, so what I can do is that I can select a region. Let's say you see this squares here, mark region. So you click here, and then left, you hold the left mouse click and draw a region. Okay, so I have marked a region, right? And I want to know the information about this region. So I can say locate. You see here this search kind of thing. Okay, if I hit locate, then in the log it gives me the information about, yes, you see. So those points you see, it is saying that it is scan 1, and it is giving the info about all the points. You know, in that box there are many points, right? So these points are coming from scan 1, which is field is 3C147, time stamp is this, you know, baseline is C4 and E4, spectral window 0, channel is 128, which we have already said, frequency is this, correlation is RR, we have said, and so on and so forth, right? So it is basically when we are, so see, finding a dead antenna is very easy, you just go through and do it. But there would be times, that is the challenge, that many times antennas do funny things, or you know, somebody went and switch on his mobile phone, right? So those kind of bad things will be temporary, and they will not be present in all the antennas. You know, I standing in some antennas, I will just open, so that antenna will be affected. So your job, which is a very tedious work, to find out that in what time range which antenna is affected. So when you browse through this data and you look something funny, then this method is actually help you to understand that which antenna is actually affected, which time range. So with that, you can actually flag those time range. You don't have to flag the whole antenna. If you are flagging the whole antenna, then it's basically you are throwing out the whole data, which is good, right? So those particular things is helpful to kind of find out using this locate task, which is like one of the very important tasks when you are doing flagging, you know, flagging and this thing. So yeah, so this is fine. Up to this point, it is okay. You guys will confident enough to kind of do up to this point. Yes. Okay, great. So yeah, so we can break for lunch now. I would request you guys go, you know, take lunch and come, you know, 10-15 minutes before, I mean, with some time in hand, and give it a try. Then we'll move to the next process. Okay, next step. Okay, any questions? Any questions or comments? All right. Yeah.